let's get started. So my name is Anton Sinitskiy. I'm a graduate student here at the chemistry department of the University of Chicago, and evidently I work in the CMBS Center. One of my research projects is closely related to Markov State Models, and that's the reason why I'm standing here, going to talk about them. So first of all, I would like to remind you the definition of the Markov State Model in the way that emphasizes the connection between coarse graining and Markov State Models. After that, let's ask ourselves, why should we care about Markov State Models? What are the advantages of using them? You will hopefully be thrilled after that and eager to build your own MSM model for your research project. That will be the best moment to talk about how to build Markov State Models. And I'd like to finish with discussing Markov State Models in a wider context, and in particular to talk about the relationship between Markov State Models and the ultra-coarse graining methodology that we have been developing in this center. So the precise mathematical definition of Markov State Models is very abstract. So let me instead introduce that in a way that emphasizes the relationship between this one and coarse graining, and that better fits purposes of theoretical and computational chemists and molecular biologists. So we start with a fine-grained description of our system. That may be, for example, all Cartesian coordinates of all atoms in the protein or RNA or whatever else we're interested in, and the configuration space defined by those fine-grained degrees of freedom should be partitioned into a small number of regions, like so. So here we have only two-dimensional configuration space, which is evidently wrong because we're going to have typically the order of 3n dimensions, where n is the number of atoms in the system. But the idea is that different points in each of these regions representing different conformations of the molecule will be interpreted as the same state. So if the point representing the current state of the system is here, we say that the system is in state 1. If it's here, then again we say that it's in state 1, regardless of a little bit different geometries. Then the dynamics of the system can be represented as a series of jumps between different states. So we start with 3n continuous degrees of freedom functions of time, and we end up with only one discrete function of time. And that is evidently coarse graining, because we are decreasing the number of degrees of freedom, and also we usually use discrete time steps, and the time step in Markov State Model is usually much greater than the time step in the MT integrator. So if the partition of the configuration space into different regions makes sense from the physics of biology, then this approach has very good chances to give us a reasonable, though simplified, representation of the system. Now, is that enough? No, we're missing one key ingredient, and the key ingredient of Markov State Models is Markovianity. Markovianity means absence of memory in the system. So the future of the system depends only on the current state of the system, and it doesn't depend on the past of the system, on the way how the system arrived at a given configuration. So in terms of jumps between the states, the probability that we're going to have a jump from state I to state J doesn't depend on what happened before the system jumped into the state I. And then we can build the transition matrix, which shows us the probabilities of transitions between different states. So the assumption of Markovianity is a tricky one, and there is no guarantee that it will work for an arbitrary system. And probably this is a better way to illustrate that point instead of just introducing some abstract mathematical concepts. So this text was generated using a Markov State model. Markov State models have a very wide range of applicability. They are used in finance, in economics, in physics, in the theory of cues, and of course in chemistry and molecular biology. So here we have a Markov chain. So every word is introduced with a probability that depends only on the previous word. So you can see that locally that is quite reasonable. It makes sense that it's absolutely reasonable that before hand we had mine, or before oil we had natural, before them we have but the overall context is something schizophrenic, right? So many cases Markovianity doesn't work. It's very important to remember to remember that this may happen and to make some tests to check that your model is okay. Okay, now let's assume that we have nice Markovianity here, and in this case we can derive some very simple formulas. Let us consider an ensemble of molecules, just from the viewpoint of chemistry, a flask-filled solution of a protein, RNA, and whatever else, that denote the fraction of the molecule in state I as omega sub I. Then, yeah, this equation is a little bit distorted. So the probability to find a molecule in state I at moment delta t is the sum of probabilities that we're going to have a transition from state 1 to state 1, from state 2 to state 1, and so on and so forth. So that's summation over all possible previous states. And according to the Markovianity assumption, this formula is rather simple. So we can write similar equations for fractions of all molecules, I mean for fractions in all states in the system. So this is a nice simple representation. Then we can rewrite it in a compact form in terms of a vector of fractions of concentrations of different states. And we use here the transition matrix. Then at an arbitrary moment in time, fractions of the molecules in different states can be calculated by just iteratively applying the transition matrix to the vector of the initial state of the system. So omega at time n times delta t is p to the nth times the initial vector. Now, in most cases, except for some pathological ones, we can diagonalize the transition matrix, so that gives us this representation. And then it's a nice fact that p to the nth can be diagonalized on the same basis set as the transition matrix itself. So it's just very easy to check that if you multiply n copies of this expression, you end up with this one. So the set of eigenvectors is the same. Eigenvalues of the matrix p to the nth are just eigenvalues of the transition matrix raised to the power n. Then in the basis of eigenvectors, this equation can be rewritten as corresponding mode at moment t, which equals to n delta t, equals a diagonal matrix times the value of that vector at the initial moment in time. So that means that these modes are independent of each other, and each mode either remains constant in time if the corresponding eigen value is 1, or decreases with time if the corresponding eigenvalue is less than 1. And it's possible to prove that for the transition matrix, those eigenvalues cannot be greater than 1, so we don't have closures in the system, evidently, because the concentrations are limited there between 0 and 1. Returning from this representation to just concentrations of different states, we can see that the fractions, the population numbers of each state at an arbitrary moment of time can be represented as the equilibrium values, which is the limit in the case when time goes to infinity, plus some term that decays exponentially with time, with the characteristic time tau 1, plus the term that decays exponentially with another characteristic time, and so on and so forth. And so if we arrange those characteristic times in the decreasing order, then for long-term dynamics, we can use only a few terms in this expansion, or sometimes even only the first term. So by comparing this equation and this equation, we can derive exact formulas for the implicit timescales, tau 1, tau 2, and so on and so forth. And that will be the time step in the Markov State Model divided by the log of the corresponding eigenvalue of the transition matrix. So it's just written here in a more explicit form. So to get the longest time scale, we take the smallest by absolute value eigenvalue of the transition matrix. To get the second time scale, the second longest time scale, we take the second eigenvalue of that matrix, and so on and so forth. So, as I mentioned before, it's very important to make sure that your system is Markovian. There are lots of different tests to check that. But most of them are rather advanced from the viewpoint mathematics, and it's kind of, I don't want to discuss them here because that's an issue of mathematics and statistics and not of chemistry or physics or biology. But there is one exception. There is one very simple test that has clear, transparent physical meaning. That is comparison of the timescales obtained from the models with different time steps. So for example, if we take delta t prime 2 times greater than delta t, then the eigenvalue of this matrix will be equal to the eigenvalue of this matrix squared, and therefore log of the eigenvalue will be greater, will be twice as much as the log in this case, but delta t prime is also 2 times greater, so those guys cancel each other. So in practice, we take different delta t's, calculate the corresponding timescales, analyze the plot, and if we see a plateau on that plot, that is a sign of Markovianity in the system. There are lots of applications in different fields, as I mentioned. 4 of them taken at random. Folding or unfolding of proteins, different lipid vesicle formation, fusion, and lots of other. So just who is Mr. Markov, who invented those models? So the first article was published in 1906, and this year it's exactly 100 years since the moment when the first Markov State model was built. So he took one of the classical Russian literature texts, Eugen Onegin, that was the pronunciation, and he treated it as just a sequence of consonants and vowels. And he found that the probability to found a consonant or vowel at a certain position strongly depends on what goes before that consonant or vowel. But there is no significant correlation between that and what was 2 steps before that, 3 steps or positions before that, and so on and so forth. Once he was asked to give a definition of mathematics, and he said, mathematics is what Gauss, Chebyshev, Lyapunov, Steklov, and I have been doing. Very unusual definition. Now, why do we want to use Markov State models? one advantage of the Markov State models is that it can serve as a basis for large-scale computations, generating long MD trajectories, proteins and other biomolecules, or inorganic or organic materials. So there are two main approaches. One is folding at home, which relies on using idle computational resources of personal computers by volunteers. So you just can go to their website, download the corresponding program, it will work instead of just when you're not using your computer. And it's very important to have Markov State model here, because you cannot exchange information between different computers. And you cannot rely on those computers too much, because at some moment the user may want to start working on it and then simulations stop. So a good approach in this situation is to start different simulations from different Markov states, and the result that you get from those simulations is just the estimate of the matrix, of the elements of the transition matrix. Another approach is based on using a supercomputer, Anton, which was launched a few years ago. So they generated, they reached the timescale of milliseconds at nearly the same time. So this is a continuous MD simulation, which sometimes may be boring because the system prefers to spend time near the minimum on the energy landscape. With Markov State models, we can do adaptive sampling. So if we're interested in some observable, for example, an eigenvalue of the transition matrix, or the longest characteristic timescale, then we can expand that value, that observable, which is interesting to us, in terms of the errors that we have in each of the elements of the transition matrix. So it's just the simplest Taylor series expansion, first order expansion. We can use it only if we are near to the correct point. But this shows us that the error in the observable depends both on the error in each of the elements and sensitivity of the final result of each of those elements. So it doesn't make sense to have the same precision level for all elements of the transition matrix. Instead, you can apply this formula, find the term that contributes, that gives the biggest contribution to the error, and then to run new MD simulations starting from that Markov state, and therefore increase the precision level and reduce your error. So again, you don't need to be near the minimum of the potential energy surface. You can go to more interesting places, such as the hills. Very often people assume that a transition pathway from the value of reagents to the value of products is just a single pathway. That's an approximation, and it's not always true, of course. Markov State models can allow us to represent more complicated pathways. So, for example, here, if we start in this state and we want to end up in a folded state, then we can see that we can follow this path, or this path, or this path, and many other methods, like string method, cannot represent this. Now, how do we build Markov State models? Well, the fast and simple question is just go ahead and download software for doing that. There are lots of packages for Markov State for building and analyzing Markov State models, because the range of applications is very wide. But there are two programs that are especially designed for analyzing MD trajectories. One of them is called MSM Builder, the other one is MMON. So they both can work with GRAMACS and ambient codes output. They are both available online for free. One is developed and maintained by a group in Stanford University in the States, and the other one in Berlin in Germany, Europe. But you possibly want to be more than just a schooled monkey, and besides just pressing buttons. According to the instruction, you want to understand what's going on. So one of the keys to success in being Markov state is a correct definition of Markov states. So consider, for example, this energy landscape. If we define three states A, B, and C this way, then Markov state models will be very bad, because suppose that we start in state B, and if we're here, then most probably the next transition, the next jump will occur to state C. If we're here, then the transition will occur to state A. But if the previous state was C, then most probably we're here. And if the previous state is A, then most probably here. And so the assumption that there is no memory in the system is violated. So if we have C to B to C transition, that's more probable than A to B to C transition, vice versa. A good Markov state models will have borders between different states near a local maximum on the energy landscape. But it's nice to do it when you have the energy landscape, but typically we don't have that. And of course we have to use some other methods. One simple method is just use dimensionality reduction to project your MP trajectory on 2 or 3 most important degrees of freedom, and to look at that, to look how the point representing the state of the system cluster, probably to estimate free energy in different regions of the configuration space. And another approach is to do it in 2 steps. First, to use structural data to cluster all the information into maybe 100 or 1,000 clusters. And after that, to use kinetic information to refine the model and to join those clusters to get bigger clusters. So this is an illustration of the first method. So we just project all fine-grained variables on the space of 2 most important degrees of freedom. So we observe one minimum here and another local minimum here. If you look at that, it probably makes sense for you to define 2 states. You have some separating barrier between them, and so that gives you a good model. Alternatively, you can do a 2-step process. On the first step, you cluster your configurations based on some distance metric. Most typically that's RMSD. And on the second stage, you join. So you have to join them, because if you have 1,000 or 100 states, you cannot analyze them, and there is huge uncertainty in the elements of the transition. So instead, you group those clusters into bigger ones in such a way that the transitions between those mega clusters are rare. So automatic state decomposition, just that means definition of the states, or the states, can sometimes lead to garbage, sometimes can lead to very interesting results. So I would say the first situation is probably more typical, but my illustration is about the second situation, when automatic state decomposition based on some probably artificial intelligence codes for dimensionality reduction, clustering, that's kinetic clustering. So they considered this short peptide that with 3 amino acids. They introduced 2 collective variables, which are just 2 dihedral angles, which makes sense for peptides and proteins. They projected all points in the configuration space that the system has intended onto these 2 dimensions, and they color them according to the Markov state to which they are assigned. And so here you have a nice separation of this Markov state from other other clusters, and it's reasonable to assume. So you can see that the transitions between this cluster and the neighboring clusters are relatively rare. So the system had enough time to equilibrate within that cluster. But this or doesn't look so good because we have mixture of pink and black points there. So at first sight, you might think that the method failed, but more detailed analysis showed that it didn't fail, but gave us some additional knowledge. So it turned out that these two types of conformations are very different in terms of this angle, which is as omega here. So there is one more essential degree of freedom in this system that we initially, that the authors of that work initially ignored, but were able to find using some automatic calculators. And so finally, let's talk about Markov State Models in a wider context. So that's evidently not the only method to be used in computational biology. There are some drawbacks and limitations. One evident limitation that you may have insufficient sampling, and in that case, everything goes wrong. So you may be missing some of the Markov states, and in that case, instead of the full transition matrix, you have a smaller transition matrix, and that evidently affects all eigenvalues, eigenvectors, timescales. Or even if you have all Markov states in your model, the required timescale of simulations may be not enough to sample the elements of the transition matrix. Another problem is that force fields may be not accurate enough. So that's a problem for any method in computational chemistry or computational biophysics. So why do we need to mention that explicitly here? The problem is that force fields, so the problem is that molecules are described by quantum mechanics and not by classical mechanics. And when we run our MD simulations with classical force fields, with maybe 2 body terms and sometimes a little bit of 3 body terms, but ignore higher order contributions, the result may be only, it may only resemble what we have in the real system. And the problem here is that this correspondence may break under different circumstances, including the length of the trajectory. So you may have a situation when your force field works nicely on the time scale of 10 nanoseconds, 100 nanoseconds, but leads to absolutely unreasonable results on the time scale of 1 millisecond. And since Markov State models allow us to go beyond what's available in ordinary MD simulations, this difference may be important. Direct comparison with experiments may be problematic. So sometimes you cannot see those states in experiments. State decomposition may lead to strange, weird results. So you always have to look at those states with your eyes to make sure that it makes sense from the viewpoint of physics and biology. The assumption of Markovianity may be not valid, as I told you. One more problem is that if you have several molecules in your system, and you have a Markov state model for each of those molecules, then you have a combinatorial explosion of possible interactions. So you have, let's say, 20 states in one molecule, 30 states in another molecule, and so to describe interactions between them, you have to consider 20 times 30, that means 600 variants. And if you add third molecule, that will be multiplication by one more vector of 20 or 30, and that's not good. So the relationship between Markov state models and ultra-coarse graining. So our main object of research is active filament. It is built out of active monomers. So we might use a 4-domain model, for example, for that, or other models, and we can introduce discrete variables to reflect the state of the D loop there, or the state of the bomb nucleotide. And Markov state models are very good for modeling folding or unfolding events. So we can use something like a Markov State model to describe what's going on this D loop, but there are lots of D loops shown in red here. So you have a combination of lots of Markov State models for each D loop, probably each nucleotide, and you may have to. So now you can introduce the coupling between discrete and continuous degrees of freedom. So the probability, the transition matrix may depend on the distance between this coarse grain side and this coarse grain side, or this coarse grain side and another coarse grain side in the neighboring molecule, and so on and so forth. And there are some experiments that tell us that the probability of transition between different states depend on the degree of flattening effect. So we have to use only a few states here to avoid that internal explosion. But this refines our model in the sense that now we have the dependence of the transitions on the continuous degrees of freedom, and vice versa, the potential of interaction between beats on the Markov states in an explicit form. So the take-home message from this, the only thing that you might want to remember if you don't remember everything else, is that Markov state models work sometimes very well to describe long timescale dynamics of the system based on shorter timescale events, that is transitions between states, but you should be very careful with applying them and not applying them when the system is not Markovian. So I'm very grateful to my colleagues with whom I work on this project, and my special thanks are to Nina Hendricks, who was a professor here in the University of Chicago, but recently moved to Google. She gave a lecture on Markov state models at a similar workshop 1 year ago, and actually the overlap between my lecture is not too big, maybe 1/4 or 1/5. So you may want to go to YouTube and watch her lecture as well, which may give you some more information on this topic. That's it, thanks. Any questions?